So I will start with a very quick glance at what we are researching, and then go to how we stored the data in a fair way. And yeah, here you can see a screenshot of the publication to which the data is associated. It's called Predictive Design of Ordered Mesoporous Silica with Well-Defined Ultra-Large Pores. And yeah, as mentioned already, I came back to the University of Stuttgart to work in the CRC there. And the idea of the CRC is to do catalysis within confined geometries. So to kind of mimic the pocket of an enzyme with this confined geometry. And for this, we are synthesizing mesoporous materials. So for us, it's really important to make materials with very defined mesopore diameters, and also to have a broad range of different diameters so that we really can study confinement effects. And for this, we use a tool which is called True Liquid Crystal Templating, which is quite nice because you can use the knowledge which is already available from liquid crystals and transfer it to the mesoporous materials which you make. However, there are two challenges which we wanted to tackle with this study. And the first one is that it's very difficult to make mesoporous materials with pore sizes larger than 10 nanometers with this method, because commercially only so and so big surfactant molecules are available. And so with this, you can maybe make pore sizes up to 7 nanometers. And the second challenge is that if you want to make new ordered mesoporous silica materials, it's quite difficult to predict what you have to do to get a certain pore size. So it's a lot based on trial and error. And so the objective of our work was to develop a method with which you can rationally address certain pore sizes, and also to increase the accessible pore size range up to about 20 nanometers. And then later on, these materials are then used by our collaborators within the CRC 1333 as support materials for the molecular heterogeneous catalysis. Yeah, and the first step which we had to do was to synthesize amphiphilic molecules which we can use as surfactants, which have a higher molar mass. This was done in the group of Dr. Stefan Naumann, who's also a co-author of the paper, of course. And so he developed a method with which you can produce this reverse type fluoronics with this polypropylene units here in red, polyethylene oxide units in blue, and then again the polypropylene oxide. So you have the hydrophilic parts in blue and the lipophilic parts in red, making this amphiphilic molecule, which when you can fold, or imagine that you fold the molecule, you get a surfactant. And he produced them with a very high molar mass. So we could also investigate larger structures. And this molecule then we used, or this kind of molecules, in the True Liquid Crystal Templating, where we mix it with water and a silica precursor, and then due to a self-assembly process, an intermediary liquid crystal phase is formed. So here we have elongated micelles which order on a hexagonal lattice, and we have the colloidal silica surrounding these micelles. And then if the colloidal silica starts to polycondensate, we get a hybrid material where the pores are still filled with the surfactant, which then has to be removed, for example, by calcination or by extraction, to then give us an ordered mesoporous silica material. So, and with this method and these new reverse pluronics, we were then able to synthesize a large variety of different mesoporous materials. Here you can see some transmission electron micrographs. For example, here you can see this hexagonal arrangement of the mesopores. And here in this other part, this is a side view of the pores showing that they're parallel, like tube-like structures. And then, of course, we have them with different pore sizes. And of course, we had to investigate those structures very thoroughly, as we had to investigate the polymers before also. And so the quintessence of our work is that we can adjust the pore diameter by varying the number of propylene oxide units in this reverse pluronic. And you can see here in this graph, we have a perfect correlation between the pore size and the composition of the pluronic. And you can also see that the range of pore sizes which we have here goes from about 5 up to about 21 nanometers. So this is really a large range, which was not possible to synthesize before, at least not in such a controlled way. So now let's go to the data management. And here we really have a lot of different data. As we are working in physical chemistry, of course, we do a lot of characterization. And so we have the data from the synthesis of the reverse pluronic. So there we have NMR data and gel permeation chromatography. We then have data from characterizing the mesoporous materials, for example, small angle X-ray scattering and nitrogen physisorption. And then we also have image data like the transmission electron microscopy pictures. And our goal was to store this data in a fair manner because, yeah, we also had the problem in the past that we could not get the information which we needed from the manuscript, which was published. And it was not possible to get the primary data anymore. And we wanted to make this possible in our work. So we split up our data in 3 sections. The first one is the polymer properties, where we have the GPC and NMR data. Then we have the properties of the ordered mesoporous silica with the scattering data and the physisorption. And then we have a third section, which is investigation on microporosity. This would maybe also be good to incorporate in the OMS properties. The reason why we have it separately is just because this was added later on during the revision process. And we uploaded that to DAROS, which is the dataverse of the University of Stuttgart. So here we have the possibility to store our data. And what was really important is that we created a DOI for the data on DAROS before we published the manuscript. So we could add this in the footnotes of the manuscript, and also in the supporting information, we also linked this DOI. So it's really findable. And this is now how the DAROS website looks like. You have in the beginning some description, what kind of data you have, and then you have keywords, so you can make it searchable. You have the link to the related publication, and then for our case, we also put the link to the supporting information, which is free of charge, because there is a table which will explain the denomination of our samples. And then you can also put further information on, for example, measurement methods and the kind of data files. The data can then be downloaded here in this zipped folders, as I showed before, in just 3 categories. And if you open them, you come to such folders which are named with a number and a letter. And this number and letter refers to how we denominated the samples in our manuscript. And this can be explained by the table, which was linked in the beginning. If you then open them, you get the data. So for example, here the PDF, that's the NMR data. And then if you go inside this folder, that's then the GPC data. And yeah, we tried to make the data as machine readable as possible and also as accessible as possible. For example, if it's not a format which can easily be opened by free software, we try to add a certain file as a PDF or a text file. In some cases, this is also not possible, or it was not possible to give a data file where we had like a text file as for this PDF here, which would of course also be an improvement. And this is now the table I talked about, where we have the link to how we denominated our data. So here you have all these numbers and letters, and then you can see exactly what the composition of the polymer is. And you can also see then more data or a summary of the data which we stored, and also information about the ordered mesoporous material which we fabricated from it. So to sum up, we did our very best to make our data fair by publishing it with a unique identifier, and to link it also both in the publication and the supporting information. It's possible to search the Davos Dataverse, and we have these keywords associated. We added the data in an accessible way, so it can also be used again. And also for the reuse, we made sure that we have the licensing agreement, so it is openly available upon citation. Yeah, and this is the end of my presentation. Here you can see the people who did the work. So this is Stefan Naumann, who is the group leader of a polymer group. And this is Charlotte Vogler, our mutual PhD student, who did basically all the work, I have to say. And this is Selina, who helped with preparing this presentation, and is also very involved in other projects in storing data in a fair way. So thank you very much for your attention.